If you think of lasers, a few things might come to mind. Laser cutting, laser swords, laser engraving, laser cannons. In all of these examples, lasers make things hot, but lasers can also be used to make things cold, very cold. If you're confused right now, that's understandable. Using a laser to cool something down might seem like trying to put out a candle with a flamethrower. But laser cooling actually works, and over the last 2 decades, it has become an important technique in many areas of research. So how does laser cooling work? To understand how to cool something, we first need to have a notion of what coolness is. The temperature of a substance is a measure of energy in the form of random motion of the particles that make up the substance. The higher the temperature, the more motion. If you wanted to cool something down to very cold temperatures, a good way to do it would be to make a device which can hold all of its atoms very still. This might sound impossible, but just like almost everything else, you can do this with lasers. You probably learned in high school that atoms have discrete energy levels. An atom in an excited state will eventually decay into its ground state, releasing its extra energy as a photon with a certain wavelength. Similarly, if you put a ground state atom into a beam of photons with this wavelength, the atom will occasionally absorb a photon and enter an excited state. Eventually, it will decay back into its ground state and re-emit the photon in a random direction. Since light carries momentum, if you have an atom moving in one direction and photons moving in the other direction, the atom will, on average, slow down. However, atoms only absorb light of certain wavelengths. Say you have a hydrogen atom. Hydrogen has an energy transition with a 121 nanometer wavelength. If you fired photons near this transition wavelength at the hydrogen atom, the probability of the atom absorbing any given photon depends on how close the photon's wavelength is to the transition wavelength. The closer the wavelength, the more likely the photon is to be absorbed. Specifically, the absorption probability is described by a curve called a Lorentzian, and the width of this curve is called the natural line width of the transition. Okay, so how can lasers hold atoms still? Let's consider this problem in one dimension. Say we take our hydrogen atom and shine 2 lasers on it from both sides. The lasers have a slightly longer wavelength than the transition wavelength. We call this red detuned light, since longer wavelengths appear redder. Suppose the atom is moving toward one beam and away from the other. The atom sees the wavelength of the beam it is moving toward as being blue shifted to shorter wavelengths, closer to the transition wavelength, and it sees the other beam as red shifted to longer wavelengths away from the transition wavelength. This means the atom is more likely to absorb photons from the direction it is traveling towards, reducing its momentum in that direction. The photons are re-radiated in a random direction, which has no average effect on the atom's momentum. The net effect is to reduce the overall momentum of the atom. Just like you use 2 lasers in one dimension, you can use 6 lasers in 3 dimensions to get the same effect. In a sample with many atoms, this amounts to cooling the sample by reducing the motion of its atoms, effectively holding them still with lasers. This process is called Doppler cooling, and its development, in part, won a Nobel Prize in 1997. So we can cool things down with lasers, but how cold can we get them? Suppose that the energy transition we're exploiting for Doppler cooling has a very large line width. This means that the atoms must be traveling towards a beam very fast in order to see a wavelength that is sufficiently blue shifted to the transition wavelength. If we have a small line width, then the atoms don't need to travel as quickly to blue shift the lasers toward the transition wavelength. So you might expect the minimum average velocity of the laser-cooled atoms to scale with the transition line width, and you'd be correct. The coldest temperature you can cool a substance to with Doppler cooling is called the Doppler temperature, and it is proportional to the line width of the transition. For most substances, the Doppler temperature is a few hundred microkelvin. If you want to cool things down even colder than this, you can use any of a variety of techniques in sub-Doppler cooling, including Sisyphus cooling, phase lensing, and cooling with laser-painted potentials. But those are topics for another video. Laser cooling has tons of applications. If you want to study quantum mechanical properties of macroscopic objects, you can create a Bose-Einstein condensate by cooling them down to very cold temperatures. You can also use laser-cooled atoms in a technique called atom interferometry. Researchers at Stanford are building a miniature gravitational wave detector based on this technique. Laser cooling is also an integral part of many quantum information experiments and is sometimes used in prototype quantum computers. Finally, the super-precise atomic clocks that make GPS possible are based on hyperfine energy transitions from laser-cooled atoms. So not only can lasers heat things up, but they can also cool them down. And that's pretty cool.